Hello everyone, this is Joe with Joe Talks, and today we are going to go over a calculation of a front position analysis of a short long arm front suspension on a race car. And particularly in our example, we're going to do it for a dirt late model, but this example could be used on any kind of short long arm front suspension. And now this video is actually a part two of a series that I'm doing on these front suspension geometry analysis. There was another video I did where we went through the same kind of process, but we used a trilateration process. Some people might commonly heard that referred to as the GPS method. It's just using that same type of calculation. And in this video, we're going to do that same type of calculation, but we are going to use some numerical methods. So if you haven't seen that last video, I encourage you to go back and take a look at it. That kind of spells out what we're going to do and gives you that same example. But just real quickly, a recap of what we're doing here. If we look at the front end of a race car, we are going to calculate the position of the upper ball joint, the lower ball joint, the outer tie rod, and then 2 points along the spindle axis. So we have those 5 points that we're going to calculate, and then along with the lower shock position. And if you watched that video, we talked about how this is a function of the shock length and the inner tie rod position. And so we can put our shock at any position, put our inner tie rod at any position, and know at any point in time what the position of those 5 points on that spindle are. And then using those 5 points, you can calculate your camber, caster, toe, scrub radius, anything else on that front suspension that you are interested in. And again, this is really handy if you're using a data acquisition where you have a linear pot on your shock and on your tie rod so that you know what those positions are at any given time. One thing I will point out that these calculations are in the chassis coordinate system, and if you're getting data from your car and you want to calculate things like camber or caster, you're going to want to know what the roll and the pitch of the car is at any given time and offset those accordingly. Just keep that in mind that these numbers, again, are in the chassis coordinate system, not the ground coordinate system or earth coordinate system. So now, just real quick, just to review these points that we're going to use as inputs into this function, we have on the lower control arm, we have the front and rear mounting points, the lower shock, the lower ball joint, and then on the upper control arm, we have the front and rear mounting points and the upper ball joint. So if you remember in the last video, we had to identify some points on our local coordinate system of each of the parts that are in our system. So in our system, in this front suspension, we have the chassis itself, again, the upper and the lower control arm and the spindle. And so we have to go and measure those points like on a bench top somewhere and figure out where those points are in 3D space in those components' local coordinate system. And I've done that previously. I'm not going to go through how you would make those measurements in this video, but just keep in mind that you could set up and make kind of a custom coordinate measuring machine using some just basic rails and lasers, and you could measure those points in 3D space. Now, one of the things that we are going to have to do is map out our points and give these points some definition. So I've done that here, and I've created points with numeric identifications. And one of the other things I want to point out, in our previous video, we only did the right front suspension. In this video, I'm going to actually do both the left and the right front all in the same system of equations. So as we look at these points here, you're going to see 2 points. So one of the points are for the left side of the car, and the other point is going to be for the right side of the car. And so I have those spelled out here. And I've just kind of roughly drawn out some points, and each one of these pages is going to represent a local coordinate system for each one of those components in our system, in our suspension. So What we're looking at here are the chassis points, and I've got the left and the right side um, kind of identified over here. These are the same points in our previous video. So we have point 3 is the front upper control arm. Point 2 is the rear upper control arm. Point 1 is the upper shock mount. Point 5 is the front lower control arm. Point 4 is the rear lower control arm. And then point 6 is the inner tie rod. And then those same numbers for the left and the right side. And then for the upper control arm, we need to measure the 3 points, the front, the rear mount, and the upper ball joint. And again, each one of these points, we need a measurement point in that local coordinate system. So you're going to have a point definition for the front mount, the rear mount, and the ball joint. And then conversely for the left and the right side. And then again, with the lower ball control arm, the same thing. You've got the front mount, the rear mount, the lower ball joint, and then the lower shock. And again, all of these points are going to be in that local coordinate system. So again, something you can measure on a bench top or something like that. And then for the spindle, same thing. We've got at the upper ball joint, lower ball joint, the outer tie rod, and then an inner spindle and an outer spindle point. Each one of these points get a numeric identification. So now that we've mapped out and identified all of the points that we're going to use in our system, I want to show you real quick in the program where I've entered those values. So if you remember in the last video, I talked about how you could do that trilateration process. You could probably do that in Excel if you wanted to. I like to use Python. The approach that we're doing in this video is not something you're really going to be able to do in Excel. So you're going to need a program like Python or maybe MATLAB or something where you can actually write the code to do what we need to do here. So what I want to show you is some of the code that I've written, and can feel free to copy this if you want. I don't care. It doesn't matter to me. So what I've got here is one of the pages that I'm using in my Python script to do this calculation. And in this page, I'm simply entering the points that we previously identified in our PowerPoint screens earlier. So as you see here, just doing some basic Python importing. We use NumPy and SciPy. Those are just some Python packages, and they're going to be used throughout this process. So keep in mind that you'll want to make sure you import those. If you download Anaconda, which is a kind of a generic Python package, it's all free. They come with NumPy and SciPy already installed. So just keep in mind you will have to import those. And so right here, I'm simply initializing some arrays that with 0 values, and then I'll go back and overwrite those with valid values. So I've got one of the arrays I've just identified with the letter P for points, and another one for L for links, and we're going to talk about links here in just a second. And then I've got some offset values, and the only reason I put these offset values in are if I were to ever go back and remeasure the car for any reason. You know, you're never going to get a car set up in the exact same position, but if you can figure out what the offset is, you could put those in here and then offset all these points to a new position that you have a car sitting in your shop for whatever reason. So right now the offsets are just all set to 0, so they're not really relevant to what we're doing here. I just included them in the program. But anyway, right here you see, again, one of the things similarly to what we did in the other video, I set up a 3-dimensional array for our points array. It's 37 rows long by 3 columns by 2 deep, two positions deep. And those positions, for the first position is the point identification, and then the second is the axis, so a 0 for X, a 1 for Y, a 2 for Z. And then the third position is to identify if it's in the chassis coordinate system, or if it's in a local coordinate system. And so that's what you see here. For example, for point 1, so the 1 is the point, and then the 0 is the x-axis, and the 0 is in the chassis coordinate system. And then same thing for y, same thing for z. And so for those points that are on the chassis from the first screen that we looked at earlier, we've identified the chassis pickup points, and that's what I've entered in here for the left side, and again for the right side. And so if you remember, these points correspond to the points that we just talked about a few moments ago. And then for the upper control arm, same thing. I've got the point identification, the 0, the 1, or the 2 for the x, y, and z, and then a 1 to indicate that this is in a local coordinate system. And I just put that in there just to keep things a little clean. You may not need that, but I just did for housekeeping purposes. So again, we have the left side, the right side. Same thing with the lower coordinate system, or the lower control arm. And then the same thing for the spindles. And so these are just those local points that, again, you would measure out on a bench top somewhere. Or if you have some money and a good CMM machine, you can go measure them on a coordinate measurement machine if you have those resources. So, okay. So now that we've talked about the points, again, if you remember in the last video, we also need to know the distance between those points. And so that isn't something we have to measure. Once we have the points measured, the points themselves, we can calculate the distances. But we have to tell the system what those links are, and then those are going to be used as inputs to our solution in our code. So just real quick, let's take a look at those. So for the upper control arm, for example, just simply the distance between the front mount and the upper ball joint. Same thing for the rear, the distance between the rear to the ball joint. But I just gave each one of those links, again, a numerical identification, just so we can map out what these values that we're going to use later on. So the upper ball joint, lower ball, or lower, said up, not upper ball joint, the upper control arm, lower control arm. Again, the distance between the front mount and the lower shock, the front mount and the lower ball joint, the rear mount and the lower shock, and the rear mount and the lower ball joint. Again, these are all calculated values based off of those measured points. And then same thing for the spindle, just distances between upper ball joint and outer tie rod, upper ball joint, inner spindle, upper ball joint, outer spindle, so on and so forth. I'm not going to spell all those links out, but you can see in the diagram there, you get the general idea. And again, we just simply use Pythagorean's theorem to calculate those distances. And so if we come back over here to our code in those inputs, I mentioned earlier, I had that array that I called L for links. And so down here, you can see where we're simply making the calculations for each one of those links that we just identified in our pages. And so every one of these are simply using Pythagorean's theorem to calculate those. And again, you're welcome to copy this or replicate it. I don't mind. And then the final links that we need are the shock links. So shock length for the left shock, shock length for the right shock, and then also the length of the tie rod itself. So all of those values are just values that we'll enter in to the last 4 positions of that L array. And then those are going to be used as inputs to our calculation. So now that we have all of our points and our associated links defined, let's talk a little bit about how we're going to solve for these positions. So the solution method we're going to use are some numerical methods. So one thing you might have noticed in those calculations is that none of those were linear equations. Those were all non-linear equations. So we can't use just good old matrix math or linear algebra to solve those systems of equations. We have to use some numerical methods. And so we are going to use some tools in the SciPy package, specifically in the optimize libraries, and we're going to use the least squares method to solve for these systems of nonlinear equations. And so let's take a real quick look at that. So this is the uh, SciPy optimized least squares function, and so as you can see, there's quite a few inputs to this function. Um, don't let those scare you off. Most of those we're just going to use the default values, but the ones that we are going to use specifically are the function input to this function. uh, a series of initial guesses. So anytime you, well, specifically with this approach, with a numerical method, you have to give the system an initial guess, and then it's going to go through an iterative process and converge on a solution for all of the unknowns in your system of equations. And then we also have to pass it the arguments, specifically in our case, that P and L array that we just talked about. And then we're also going to set the full output to true. I think that's the default value actually. And then we also have to give the function a tolerance limit. So this is going to go through that iterative process, and it's going to try to converge on a solution. And so we have to give it a tolerance band to say when good enough is good enough. And so we just have to say, okay, once our error in our solution gets down to a small enough value, we're just going to accept those results as accurate values. And so those are the only inputs we're going to use, and everything else in this function we're just going to leave at the default values. Okay, so now that we are somewhat familiar with the least squares function in Python, let's talk a little bit about those inputs that we're going to use. So that first input, the function input, that is a series of equations in a vector form that we're going to pass into this least squares function. And so you might say, well, what are these what is this vector of equations that we're going to use? Well, these are the equations that define all of our components. And specifically, it is basically the same form of the equations that we used to calculate those links values earlier in our input page. Now, in that scenario, we knew all of the points on our components, and we had to calculate the links. Now, in our solution set of equations, it's just the opposite. We know the links, but we don't know the points. And so those points become the unknowns in our equations, and the links become the known values. And so we have to establish that set of equations to be used as the input to our least squares functions. Now, one thing we have to do is we have to we have to develop a vector of unknown quantities. So let's take a real quick look at that. So if we come over here, let's take a look at the map of points that I've made for our unknown values. So what we are going to have is a 36 position vector of unknowns that we're going to solve for. And so what we've got here is the upper ball joint, lower shock, outer tie rod, inner spindle, and outer spindle. So those 5 points on the spindle plus the lower shock position are the points that we're going to solve for. Now, one of the things you might notice here that's different from the way I set up the array, where I had a single position in the array and then use the columns and the depth to establish the XYZ points and the chassis or local coordinate points. In this vector, we can't really consolidate that down to a single point in our array. So what we do is we specify a specific point in that vector to be an X position, the next point the Y, the next point the Z. And so that's what you see here. So like for our ball joint position, we have our X, Y, and Z. So that is point 0, 1, and 2. For the lower ball joint, X, Y, and Z is 3, 4, and 5. so on and so forth for all of the points that we're going to solve for. And then we end up with this 36 position vector that we're going to use and reference in our system of equations that we're going to pass into our least squares function. So let's take a real quick look at that system of equations that we built. So this is a second page that we're going to use in our overall code to make this solution. And so again, in this page, we've imported the numpy package. We imported the least squares from the SciPy optimized package. And we're going to reference those later on in the code. So what we are doing is we are creating a function, an overall function that we're going to pass that P array, the L array, and then our initial guesses to. And then we're going to inside of that function, we're going to create a sub-function that's going to contain all of our equations that we're going to pass into this least squares function. So specifically what I want to look at right here is this sub-function. And so you can see right here, I'm passing in my an initial 36 position array, and defining that as x, and so that's equivalent to that x vector that we just talked about. And I'm kind of using the term array and vector interchangeably. When I use array for a vector, I'm meaning a single dimension array. And so we're going to pass that empty, or pass that array, and that's going to be our unknown values. And then we're going to pass the P and L, and we're going to wrap those up into an input variable and pass that into the function right here. So I've created a variable called Kelly, and that happens to be my wife's name, just kind of getting creative with some variable names. And we're going to pass that into this internal function that I've just called func for function. And so as you can see right here, this is that Pythagorean's theorem. And so what we've done here is we've just passed our known value for the length and then our unknown values that we want to solve for. And so as you can see, we've done that for each one of these known lengths. And so you'll notice these basically take the same form of those equations that we used in our local coordinate system. It's just now we are solving those in the chassis coordinate system. So that's another point on these unknown values in this x vector, is that these are all going to be solved in the chassis coordinate system. And so it's going to give us all those points, and then anytime our shock length moves, we're going to recalculate and re-establish what those unknown values are. And so that's what we've done here. So this is for the lower control arm. You see the same systems of equation here. The right lower control arm, same thing with the left spindle, the right spindle, the left upper control arm, right lower control arm. Again, we've just replicated those length calculations, except now we're using the known value of the length and the unknown points that we use to establish that length. And then you also notice that previously, like in a Pythagorean's theorem, it would just be square root of the x squared minus y squared minus z squared equals the length. Well, we've taken that length value and put all of those on the same side of the equation sign and made those all equal to 0. But instead of being equal to 0, those are equal to this position of our f equations vector. And that is the f equations vector that you see right here is what we're going to pass into the least squares function in our Python code. And then down here you see I have assigned all of the guesses to another vector right here, and I've designated that as x0 or x0. And then right here is where we actually input those values into our least square function. And so right here I'm calling this internal function, And this internal function returns this vector of all of these equations of unknown values. And then we also pass our vector of guesses right here. And then we pass in our arguments. And then again, our arguments are this P and L array that we established in our input page. So, and then we set our full output to 0. And then we set our tolerance. And so you basically set your tolerance at some obnoxiously low value. So right here, I've got it set to about 1.5 to the negative 8. So that's 0.000 something or other 15. And so extremely tight tolerances on our solution. And then that's going to ensure that we have pretty accurate results. And so we pass those values, do the calculation, and then we return all of those unknown points in a solution vector that we've identified with the variable named Joe. So my name Joe. And we return that as the output of this overall function. And then to call this function, I want to back up real quick and just show you right here where I established all of our guesses. And so these are all of the initial guesses for the points. And one thing to note about your initial guesses is they don't have to be spot on or anywhere close. They just kind of have to be in the general vicinity. One thing I will want to point out is you do want to be mindful of where you start your initial guess, because if you have any components that could technically be installed upside down, depending on what direction the solution approaches that final result, it could find one of two possible solutions. So if you remember back in our trilateration process, you remember where I pointed out that there's actually two possible solutions, and you just have to be mindful of which solution you're using. So we have the same thing here. We have certain situations where there could be two possible solutions within this equation output. And so a good example of that would be the lower control arm. So if you think about the lower control arm, you've just basically got the mounting points to the chassis, the lower ball joint, and then the lower shock. And typically that lower shock is going to set on one side or other of the plane that is made by the inner mounts in the lower ball joint. And so technically, that lower ball joint could fall on either side of that plane. And so you want to be mindful of where you make your initial guess for that lower shock. And so if that lower shock actually sets above the plane, you want to start from above the plane and work your way down to that solution point that's above the plane. Or vice versa, if your lower shock is below the plane, you want to start from the bottom and converge up to that point. So just something to be mindful of when you create your system of guesses. If you're getting values in your solution output that don't make sense, that might be a good first place to go look to see if you're converging on one of the alternate solutions possibilities coming from this equation. And so here is just an example where I've got those guesses in a separate page, and then in our solution process, we just call those pages and reference those values in the other pages. And so that's just a Python thing. Okay, now right here is where I'm actually calling the function. And so if you notice, I've got an import here called kinematics front, another one where I'm importing those pages, the input points and the guess points. So those are the pages we talked about previously. But the kinematic front is another page where I've kind of embedded the function that actually runs this whole process. So right here we see kin front. The input to that equation is, our input to that function is the input points and the guess points. And then down here I'm initializing a vector or a single dimension array to hold the 12 points that we're going to solve for. So the 6 on the right and the 6 on the left. And then, so we call this function, it runs the front equations function in this other page that we just talked about earlier. And then that returns, as we talked about, the results vector Joe. And over here, so that gets assigned to this variable right here. And then I just simply kind of regroup those back into another array where I can split out each individual point and the x and y position. And so that's what we see right here. So for example, point 0, x, y, z, point 1, x, y, z, so on and so forth. And then to call this function, I just embedded that into a second page. And so obviously now you kind of see the pattern. If you're not familiar with Python, you can reference things in different pages just to kind of help keep things organized. But right here, this is where I'm calling that kinematics front function, and then I'm referencing that input points page and the guess points page and using those as inputs to that kinematic front function. Okay, so let's come back over here to our spider console. And so if you remember from the other video, the spider console is just what we use to run our Python script. And so as we can see right here, I have the one page loaded where I'm calling the script. So what you see on this screen is the same thing as this file, because those are actually the exact same file. And so I can run this script, and it's going to go through all of those steps that we talked about earlier. And here we have our output. And so what we see here, this is just some messaging, some error proofing stuff, but what we see here are the 6 points on both sides of the vehicle. So we have the left ball joint, lower ball joint, lower shock, outer tie rod, inner spindle, outer spindle, and then the same thing replicated for the right side. And then these 3 values over here are the x coordinate, the y coordinate, and the z coordinate. So let's go back over and we'll just review real quick what our inputs were. So our inputs for our shocks were at left side shock 14.5 and the right side shock at 17. And then the left side tie rod at 16 inches or 16, and then right side tie rod at 19. Okay, so let's come back over here to our model in Inventor, and let's just take a look back and we'll verify. We've got our left tie rod at 16, left front shock at 14.5, right front shock at 17, and right front tie rod at 19. And so let's just compare some of these values and just see what we come up with. So let's take a look at the say left lower shock. And so there we're at let's bring these over. We're at 51,813, and right here 51,813, 21,875, and 1827. And so it looks like everything is the same. Let's come back over here and let's just try maybe the upper ball joint. So there we are at 5205. So these values right here is what we're looking at. 5205, 24,937, 31,238. So it looks like the left side is pretty good. Let's go back over here and let's pull up some values for the right side, just see where we're at. Let's try the outer tie rod here. Okay, so over here we're going to be interested in the right side outer tie rod. And we're at 56,117 minus 26,668 and 21,067. And let's just try another value over here. Try that right side. Let's look at the upper ball joint. So Come back over here. Right side upper ball joint. We're at 48,368 minus 23,512, 29,669. Okay. So looks like everything is running pretty good. Let's try changing some of those values. Let's put the say we'll put the left front at 16 and put the right front shock at I don't know, 17 and a half maybe. Just randomly selecting some values, and maybe we'll change the tie rod to be 17 and maybe shorten the right one up to 18 or something. Let's see. And so let's come back over here and we'll change our model values here. Or we changed our, let's see, close this. Changed our left front tie rod to be 17. Changed our left front shock to be 16. Changed our right front shock to be what was that, 17.5. And our right front tie rod, we shortened that to 18. Right, so 17 and a half, 18, 17, 16. Okay. Okay, so let's come back over here and we'll run that script with the new values. And let's come back over here, we'll measure those up, maybe an upper ball joint. Let's try the left front spindle. And so let's bring this back over here and we'll take a look at those values. We've got 50,208, 25,606, and 29,374. Okay, so the left side looks good. Let's come back over here and let's measure. Let's pick a value on the right side. We'll do the right side upper ball joint. Actually, let's do the right side outer spindle. Let's see if it lines up here. So we'll come back over here. Look at that outer spindle right here, 5568 minus 36,261 and 22,179. Okay, so pretty close. And right there you saw where we changed both the shock values and the inner tie rods, and we were able to pick up the changes in all of those spindle points and lower shock mounts, and see really to the thousandths of an inch accuracy, even compared to Inventor, what we could do in Python. And again, the beautiful thing about Python is it's free. All you got to do is learn how to program. So there are just a couple of things that I want to point out in this code that we wrote. And I didn't point this out before because I didn't want to introduce a bunch of confusion to what we were doing. I wanted to show the process and show how it worked and demonstrate it. But I want to go back and point out just a couple of things in our code here. So one of the things I did when setting up these equations in our front equations page where we set up that func value, if you look at these equations right here, if you think about what these are actually rigid body constraints. And so what we're using in this process is a system called multibody dynamics or multibody kinematics. And when you set up equations using that approach, you know, the first step is to set up the rigid body constraints. And really that's what we were doing with all of those local points, is we were defining the shape of the bodies that were in our system. But if you think about what's going on there, in 3D space, we've defined those bodies, but we haven't really connected anything. And so there's another step in that whole process where you would also incorporate joint constraints. And so a good example of that would be taking the spindle ball joint point and the upper control arm ball joint point and constraining those to be on the same point. And that's a pretty simple equation. I mean, it's just the x value from point A to the x value of point B are equal, y is equal to y, z is equal to z, and you're basically mathematically saying those 2 points are the same. And one of the things I did when we set up these funcs, or this function or func inner sub function, is I kind of made a shortcut. And so what I want to show right here is, instead of using an unknown value to define uh, like the chassis pickup point, and an unknown value for like the inner tie rod, instead of using a joint constraint, I just did a shortcut and replaced the unknown point with my known point. And so that's what you see right here. And in this equation, um, that's where I've introduced some known points. So I kind of bypassed the joint constraints, but I just wanted to be clear that uh, in reality, in the outside of this application, if you were doing multi-body dynamics, you would actually define the bodies and then define the joint constraints. And I just wanted to point out that I kind of bypassed that step when setting up those functions, the input function vector for our least squares function. Okay, so there you have it. There is a numerical methods approach to doing a full position analysis on a front suspension of a race car, and in this application, particularly a dirt late model. And so at this point now, we've got two different approaches you can use. You can use the trilateration GPS method, and you can use this numerical methods. And so really, you might ask, well, which one of those are better or worse? Well, it depends on your application. Like I said, if you're not really good at programming and maybe all you have is Excel to work with, you might want to try using the trilateration function or process. But if you're pretty good at programming and you want to try to use the numerical methods, maybe that's the better approach. One of the benefits of using the numerical methods is you're not limited to just doing a position analysis. So say, for example, you wanted to pick up some velocities at different points of your suspension. Well, you could very easily, take those position equations, take the first derivative, now you've got your velocity equation, and you could incorporate that into your system of equations. And so that gives you a little bit more flexibility on some things you can do in your analysis. But as far as just doing position analysis, I don't know that one's really any better than the other. It's just whatever suits your fancy, So anyway, I hope that helps, and I hope somebody gets some use out of this. I sure would like to hear some stories if anybody uses this in their applications or in their race car teams. I sure would like to hear about that stuff. And again, if you found this stuff helpful or you found it entertaining, please help me out and subscribe to my channel and hit the like button and all that good stuff. Really helps us out. So uh, anyway, that's it. And our next video in this little series is we're going to take this same type of application and we are going to apply it to the rear suspension of a dirt late model. So that'll be a good one, and be looking for that video to come out soon. And all right, and until that video comes out, thank you again, and thank you for watching. All right, thank you.